Okay, we want to talk a bit about collisions. First of all, I think you're going to see it in the homework for next time. A net force F net acting in a system changes the momentum of the system by F net delta T, where the momentum of a system is the total mass, the mass of all the particles that make up the system, times the velocity of the center of mass. And these are vector quantities, unlike kinetic energy. Now contrast this. So we want to contrast this with the idea that work is F net times delta S. And it's not times delta, it's F net dot delta S. It's not a vector quantity, because when you do a dot product, you don't get a vector. You gotta have two vectors to do a dot product. But the result is not going to be a vector. And that is your change in kinetic energy. Here, you're multiplying F net times delta T. Here we're multiplying F net by a delta S, but we're doing a dot product, okay? Now I'm going to show you just for a single particle. For a single point particle, F net equals okay, for a single point mass with a force parallel to velocity. Acceleration of the particle is F net divided by the mass. So your equation of motion, Vf squared equals V naught squared plus 2a delta x. Becomes Vf squared equals V naught squared plus 2f net over m times delta x. So at F net delta x, just a little algebra, multiply both sides by m over 2, and then subtract the term you get here from the term you get here. In other words, just solve this for F net delta x, you get one half mvs squared minus 1/2 mv naught squared. Those are your initial and final velocities. So these are your initial and final kinetic energies. That's your change in kinetic energy. So that's just an example of this when everything's in one dimension. And it's easy to extend to 2 dimensions. I'm not going to do that. we want to see how this idea contrasts with this idea. The other equation could be written as VF equals V naught plus A delta T. It's an equation that looks a lot like this, except you've got a delta T instead of a delta X. You've got a final velocity and an initial velocity instead of a squared final and initial velocity. So that's MVF minus MV naught. Kind of maybe remind you of 1/2 MVF squared and 1/2 MV naught squared, but there's just a first power and there's no 1/2. Well then, F net times delta T is the change in this MV quantity. And the MV quantity is what you call momentum. And we use the letter P by one convention to stand for momentum. And I didn't leave myself room to write it, but I'll just say P equals MV and I'll write the whole word out because it's so momentous. P equals MV equals momentum. Now this extends to multiple dimensions. V becomes a vector, and P becomes a vector. You're going to have X, Y, and Z components if you're in 3 dimensions. So that momentum, as we see, is this. So this is why we define the momentum of a system of particles as a total mass times the velocity of the center of mass. Why the velocity of the center of mass? Well, I don't want to derive it. That's just the way it is. Okay? For right now, I'd be glad to derive it for you, but we don't have time. This is particularly useful if you have a collision. Two objects collide, maybe they stick together, maybe they bounce off of each other. If they stick together, it's what you call an inelastic collision. If they bounce off of each other in such a way that the kinetic energy doesn't change, because in an inelastic collision, if they stick together, velocities or kinetic energy is always lost. Okay? If kinetic energy isn't lost, they bounce off of each other. In such a way that the kinetic energy afterwards is equal to the kinetic energy before. Regardless, in a collision, well, the objects are in contact. cannot exert equal and opposite forces on one another. If the forces are F12 and F21, now there's a convention. Now I'm going to double check the convention so that I say this right, because I have a strong tendency to say it wrong. One of those little things that I can never keep straight, because it's, actually I was confused on it, 100 years ago when I took the first semester of physics, because of the way the subscripts were being used to represent things that should have been obvious. Okay. Book finally did it right. Okay? They don't use F12 and F21. They use the thing that would have saved me a lifetime of confusion about the notation, if not the Okay, they wrote it this way. F1 on 2. That's a force exerted by mass 1 on mass 2. This is a force exerted by mass 2 on mass 1. Now I don't have to say which one acts on which. And save me having to admit there's something I just can't remember. Never been able to remember. Get something wrong the first try, tends to stay wrong. Okay. I don't know of another place where I've got a problem with notation, but that's one. Okay. A picture of this. Here we go. Okay, which one of these is F1 on 2? This point, yeah. Okay? No, sorry. That's a force exerted by F1 on 2. It's acting on, this is acting on 1, right? Okay, so if you say F2 on 1, that's a force exerted by this mass on this one. Maybe it's an electrostatic force, maybe these are magnets, whatever. So this is F2 on 1. This is F1 on 2. Well then, if your masses are M1 and M2, then acceleration 1 is force 2 acting on 1, force exerted here. And we're assuming this is a net force, assuming this is an isolated system. Now, I'm giving you an overview now. I'm not doing it rigorously because you'll get it more rigorously when you do the homework. Okay, acceleration 1, F2 on 1 divided by M1. Acceleration 2 is F1 and 2 divided by M2. More importantly, change in M1. The change in M1V. These forces are vectors, so let's do this. Okay, the change in M1V from what we just saw from the impulse momentum theorem, change in the MV is F net delta T. So we're just applying that. And that's M1V1. Okay. By the impulse momentum theorem, these forces are equal and opposite. Acting through the same time interval. All this implies center symbols for the right. So these are equal and opposite, so these are equal and opposite, and that's what I've written. If the masses are constant, change in MV is just the mass times the change in V. So I have M1 delta V1 equals negative M2 delta V2. So we'll have to start. Now, notice that everything we did there about the impulse and momentum change, the F delta T and the change in MV, just comes from Newton's second law and equations of uniformly accelerated motion. Now, officially, to derive this, you got to use intervals. Okay, so we're just doing it for constant forces on constant masses. So there's more to be done. To make everything completely rigorous, but you take this home with you. So we have equal and opposite forces, equal and opposite changes in the MV quantity. So let's draw our collision. Let's say we got this thing moving here. And I've got myself into a notational conundrum. I'm going to use U1 for the velocity. Then we got M2 U2. This is before collision. After collision, we've got M1 going to call it U1 prime, and M2 is a lot bigger than M1. It might still be moving forward, but more massive. So this is after. Your book will use different notation, but the idea is the same. What's this tell you? What's the delta V1? The change in velocity of the first mass. Well, it's a velocity it has after minus a velocity it has before. Now, U1 prime doesn't mean the derivative of U1. U1 prime is just a way of distinguishing after from before. And actually, so as to avoid that confusion, which I might have anticipated, I'll use B for before and A for after. I think that's going to be a better notation. Can we do that? So it's U1 after minus U1 before is equal to negative M2 times U2 after minus U2 before. Multiply this out. Well, I want to put all the befores on one side and all the afters on the other. I'll put the afters over here. Now, wait a minute. Yeah, I'll do that. Comes out this way. Now, M1, U1 after, M2, U2 after, that's the total momentum of the two particles after collision, right? This is a momentum of the first particle after collision. This is a momentum of the second particle after collision. Our conclusion is the total momentum is conserved if all forces are internal to the system. Another way of saying that is the total momentum of a closed system is constant. Total momentum of the universe is constant. Universe being everything. That's a closed system. There's nothing outside the universe can exert a force on it. Means its center of mass hasn't changed since the Big Bang. Yeah. Think about it. Your book will bring, your homework will bring a lot of these ideas into a greater clarity, but that's kind of an overview. I've gone in more, I think, than the homework will into the source of the impulse momentum theorem, although I think that the mastering does a pretty good job on that. I've done it in a little simpler context, actually, just particles in one dimension, equations of motion, okay? You're going to see a little bit more about it. So, be prepared to be astounded and try to enjoy the process. But one way or another, learn stuff.